If you enjoy calm, thoughtful journeys through science, take a moment to like the video and subscribe to the channel, and as you settle in, feel free to share where you're watching or listening from. After all, while this story stretches across billions of years and unimaginable distances, it always begins right where you are. Looking back is often described as something passive, as though the universe simply presents itself and a telescope quietly receives whatever arrives. But in astronomy, seeing is never passive. It is an active physical process shaped by motion, distance, and time itself. Every time light reaches an eye or a detector, something very specific has happened. A particle of light has been emitted somewhere, travelled through space, survived interactions with dust, gas, and gravity, and finally transferred its energy into matter. A telescope does not simply observe an object. It intercepts light that has been on a journey. That journey always takes time. Light does not arrive instantly, no matter how empty space may seem. Its speed is finite and fixed. Fast by everyday standards, unimaginably fast even, but still limited. This single fact quietly reshapes everything about astronomy. Because if light takes time to travel, then seeing something far away is the same as seeing it long ago. This is not a metaphor. It is not a poetic way of speaking. It is a direct consequence of physics. When light leaves a distant object, it begins a countdown, not toward decay, but toward arrival. The farther the distance, the longer that countdown lasts. By the time the light is collected by a telescope, the event that produced it is already in the past, sometimes by minutes, sometimes by years, sometimes by billions of years. This is why telescopes behave like time machines without bending space, breaking causality, or violating physics. They simply wait. The idea feels strange only because everyday life hides the effect. At human scales, light is so fast that the delay barely matters. When you look across a room, the light from the far wall reaches your eyes in a tiny fraction of a second. Even across a city, the delay is negligible. You do not feel as though you are seeing the past. But the delay is still there. Look at a distant mountain on the horizon, and the light reaching your eyes left that mountain slightly earlier than the light coming from the ground beneath your feet. The difference is tiny but real. You're already seeing a layered present, stitched together from moments that are not perfectly simultaneous. Scale that intuition upward, and the effect grows quietly dramatic. Light from the moon takes a little over 1 second to reach Earth. Light from the sun takes a bit more than 8 minutes. If the sun were to suddenly disappear, the Earth would continue orbiting an absence for those 8 minutes, unaware that anything had changed. Not because of ignorance, but because information cannot travel faster than light. Light from nearby stars takes years. Light from distant galaxies takes millions or billions of years. At those distances, the past is no longer a subtle blur. It becomes the entire view. This is where astronomy diverges from most other sciences. A biologist studies living systems as they are now. A chemist observes reactions unfolding in the present. But an astronomer never sees the universe as it exists at this moment. The universe does not offer that option. Every observation is delayed. Every image is historical. The further away the object, the older the information carried by its light. There is no clever workaround. No amount of mirror polishing or computational correction can make light arrive faster than physics allows. This sets a fundamental boundary, one that no telescope can cross. And that boundary is what makes the question of how far back we can see both meaningful and constrained. It is tempting to think of telescope power in terms of ambition. Bigger mirrors, better detectors, more sensitive instruments, and those things matter. They extend reach, they sharpen clarity, they reveal fainter details. but they do not change the basic rule. A telescope cannot see events that have not had time to send their light to us. This is why the earliest chapters of the universe are not hidden behind technological limitations, but behind physical ones. There was a time when there were no stars, no galaxies, no bright objects at all. Even if a telescope could be made infinitely perfect, there would still be nothing to see beyond a certain point. No light had yet been emitted. This is an important grounding idea, because it shifts the question away from engineering bravado and toward cosmic structure. The universe itself decides how far back observation is possible. Scientists have known this for over a century. As early as 1908, thinkers were already wrestling with the consequences of finite signal speeds. Later, through the work of figures like Albert Einstein, it became clear that space and time are intertwined in a way that makes observation inseparable from history. Distance is not just where something is, it is when it was. Modern astrophysics builds on this understanding, not by trying to defeat it, but by working within it as carefully as possible. Organizations like NASA and the European Space Agency designed telescopes with this reality in mind. Not to reach the absolute beginning, which is impossible, but to push observation as close to the earliest luminous moments as physics allows, and that distinction matters, because when people hear about seeing the early universe, it is easy to imagine peeling back layers as though time were a curtain that can be pulled aside at will. But time is not arranged like that. It does not open smoothly. It recedes in discrete steps defined by the appearance of light itself. Before the first stars formed, the universe was dark, not metaphorically, but literally. There were particles, radiation, and structure taking shape, but no glowing objects to illuminate space. No photons were being produced that could one day be collected by a telescope. So the act of looking back always involves a balance between distance and brightness, between time and detectability, between what existed and what could announce its existence through light. Even in the eras that can be observed, what reaches us is fragile. Ancient light is faint. It is spread out over vast volumes of expanding space. It arrives stretched, cooled, and thinned. Capturing it requires patience, precision, and instruments designed to listen rather than demand. This is why the idea of looking back should not feel triumphant. It should feel careful. A telescope does not conquer the past. It waits for the past to arrive. And the waiting is not passive. It involves cooling detectors to extreme temperatures so they do not overwhelm faint cosmic signals. It involves positioning observatories far from Earth's heat and interference. It involves calibrating instruments to distinguish ancient photons from background noise. All of this effort exists in service of a simple act: intercepting light that has been travelling longer than life has existed on Earth. This is also why everyday language can be misleading. When images from deep space are released, they are often described as photographs. But what you are seeing is not a snapshot of a moment. It is a collection of arrivals gathered patiently over time, each photon carrying a timestamp set billions of years ago. The universe does not send updates. It sends echoes. Understanding this changes how the question of how far back we can see should be approached. It is not about pushing harder, it is about listening longer. It is about respecting the pace set by the cosmos itself. The limits are not arbitrary, they are woven into the fabric of reality. Light moves at its speed because space-time is built that way. Information propagates the way it does because causality demands it. These are not inconveniences. They are structural features of the universe, and paradoxically, they are what make astronomy possible at all. If light travelled infinitely fast, the night sky would collapse into a confusing simultaneity. Everything would be visible at once, with no depth of time, no layered history. The universe would appear flat and static, stripped of narrative. It is because light takes time that the universe has a story. Every distant point becomes a chapter, every faint glow becomes a record, and every telescope becomes an interpreter, translating arrival times into understanding. Before considering any instrument, any mission, or any discovery, this is the foundation that must be set. Seeing is an interaction. Looking back is a physical act. And the past is not accessed by intention, but by interception. The universe reveals itself only at the speed it allows. There's a reason the speed of light appears so often in discussions about the universe. Not because it is dramatic or exotic or especially flashy, but because it quietly sets the pace for everything that can happen, be observed, or be known. Light does not merely move through space, it defines how space and time relate to one another. The speed at which light travels is not negotiable. It is not a preference of photons or a limit imposed by technology. It is a fixed property of space-time itself. No signal, no influence, no piece of information can outrun it. This single constraint governs causality, meaning the simple rule that causes must come before effects. It also governs observation, because observing something is nothing more than receiving information from it. If information takes time to travel, then the universe can never be seen all at once. This idea becomes clearer when distance and time stop being treated as separate things. In everyday life, they feel distinct. A meter is not a second. A journey across town does not feel like a journey into the past. But at cosmic scales, that intuition breaks down completely. The framework that makes sense of this was developed in the early 20th century, most famously through the work of Albert Einstein. His theories of relativity reshaped how physicists understand motion, gravity, and time. But for astronomy, one insight stands out above all others. Space and time are not independent stages on which the universe unfolds. They are woven together into a single structure. In this structure, distance is inseparable from time. To move through space is also, in a very real sense, to move through time. And when light travels across the universe, it traces paths through this combined fabric, carrying both spatial and temporal information with it. This is why the speed of light matters so much. It is not just a fast number. It is the conversion factor between space and time. It tells the universe how distance turns into delay. When astronomers say that a galaxy is billions of light years away, they are not just describing how far it is in space. They are also describing how far back in time its light began its journey. The two measurements are linked by the same constant. At small distances, this link is easy to ignore. At large distances, it becomes unavoidable. Look at a nearby star and you're seeing it years ago. Look at a distant galaxy, and you're seeing it when the universe itself was much younger. At the largest observable scales, nearly everything visible belongs to the deep past. The present moment, the universe as it exists right now, is largely hidden from view simply because its light has not yet arrived. This effect dominates astronomy in a way that has no real analogue elsewhere in science. There is no way to adjust for it. There is no correction that can be applied after the fact. The delay is built into reality, and it grows with distance. As observations extend farther and farther out, the difference between then and now becomes immense. Entire cosmic eras pass between emission and arrival. Stars are born and die. Galaxies merge and transform. The universe itself expands and cools. which introduces another subtle but crucial distinction. The age of the universe and the size of the observable universe are not the same thing. The universe is roughly 13.8 billion years old. That number describes how much time has passed since the universe emerged from its earliest hot, dense state. But the observable universe, the region from which light has had time to reach us, is much larger than 13.8 billion light-year across. This seems contradictory at first. How can something be older than its own age? The answer lies in expansion. Space itself is not static, it stretches. As light travels, the space it moves through grows. This means that the distance between where the light was emitted and where it is received increases while the light is in transit. The light did not travel faster than its allowed speed. Space simply expanded beneath it. As a result, the most distant regions we can observe today are now much farther away than 13.8 billion light-years, even though the light reaching us left those regions when the universe was much younger. This is why astronomers speak carefully about horizons. The observable universe is not everything that exists. It is everything that has had time to communicate with us since the beginning. Beyond that horizon, there may be more space, more galaxies, more structure. But no information from those regions can reach us yet, and some never will. This is not because of poor instruments. It is because of how space-time behaves. As distances grow and expansion stretches light waves, another effect becomes unavoidable. The light itself changes. As space expands, light waves are stretched along with it. Their wavelengths grow longer, their energy decreases. Visible light emitted billions of years ago arrives, not as visible light at all, but as infrared radiation. This shift is not optional. It is a direct consequence of expansion acting on light during its long journey. At small distances, the effect is modest. At cosmological distances, it becomes extreme. Light that once carried the energetic signatures of hot young stars arrives cooled, reddened, and faint. By the time it reaches Earth, it no longer sits anywhere near the range of human vision. This is where instrument design becomes inseparable from cosmic history. A telescope built to observe visible light will simply miss much of the early universe. The information is still there, but it has moved into wavelengths the instrument cannot detect. It is like trying to listen to a conversation that has drifted below the range of hearing. Turning up the volume does not help if the pitch itself has changed. Infrared detection becomes essential not because it is fashionable or advanced, but because the universe demands it. The deeper astronomers look, the more infrared the universe becomes. This is why modern observatories designed to probe the early universe focus so heavily on infrared sensitivity. They are not just looking farther, they are listening in a different register. This shift in perspective is important. It reframes the challenge of observing the early universe as one of alignment rather than conquest. The universe has already sent its messages. They are already on their way. The task is to build instruments capable of receiving them in the form they arrive. Understanding this also clarifies why there are absolute limits that no telescope can overcome. Even with perfect infrared sensitivity, even with infinite patience, observation cannot go back before light existed to carry information. The speed of light sets a hard boundary. Expansion stretches signals, and space-time itself decides which regions remain observable. This does not make the universe smaller, it makes it structured. There is a quiet elegance in this arrangement. The same rules that prevent instantaneous knowledge also preserve order. They ensure that cause precedes effect. They allow history to unfold rather than collapse into simultaneity. They give the universe depth. Without a finite speed of light, astronomy would lose its narrative. Everything would arrive at once. The night sky would flatten into confusion. There would be no sense of development, no layered past, no unfolding story written across distance. Because light is limited, the universe can be read. Each observation becomes a slice through time. Each image becomes a record of what once was. And each increase in observational reach carries astronomers not just farther away, but deeper into the universe's own history. This is why the speed of light is not merely a number to be memorized. It is the rule that gives the cosmos its shape. At first glance, the universe appears calm and still. The stars hold their positions. The constellations barely change. Even galaxies, when seen through a telescope, seem frozen in place. But this sense of stillness is deeply misleading. On the larger scales, the universe is in motion everywhere at once. This realization did not come easily. In the early 20th century, many astronomers assumed the universe was static and eternal, neither growing nor shrinking. Galaxies were thought to be fixed islands of stars, embedded in an unchanging cosmic backdrop. Space itself was treated as a passive stage, not an active participant. That picture began to change through careful observation, not dramatic theory. In the 1920s, Edwin Hubble studied distant galaxies and noticed a remarkable pattern. The farther away a galaxy appeared, the faster it seemed to be moving away from Earth. Nearby galaxies drifted slowly. Distant ones receded rapidly. Very distant ones appeared to be fleeing at astonishing speeds. At first, this looked like a cosmic explosion, with galaxies rushing outward from a central point. But that interpretation did not survive closer scrutiny. There was no center. Every galaxy saw the same pattern. From any location, other galaxies appeared to be moving away. The only explanation that fit the data was more subtle and far more profound. Space itself was expanding. This distinction matters. Galaxies are not racing through space like debris from a blast. Instead, the distances between galaxies increase because the space between them stretches. Each galaxy remains relatively stationary within its local region, while the cosmic fabric beneath them grows. A helpful way to imagine this is to picture dots drawn on the surface of a slowly inflating balloon. As the balloon expands, the dots move farther apart. No dot is special. No dot sits at the center. Each dot sees all the others receding. The balloon is not a perfect analogy, but it captures the key idea. Expansion is not something happening inside space. It is something happening to space. Once this became clear, another consequence followed naturally. If space expands while light is traveling through it, then the light itself must be affected. Light moves as a wave. As space stretches, the wave is stretched with it. The distance between successive peaks grows longer. The light shifts toward longer wavelengths. This stretching is known as redshift. The term comes from visible light, where longer wavelengths appear redder to the human eye. But redshift is not limited to visible colors. It applies across the entire spectrum. Light that begins its journey as energetic ultraviolet radiation can arrive as visible light. Light that begins as visible can arrive as infrared. Light that begins as infrared can be stretched into radio waves. The key point is that the light does not disappear. It does not weaken because it is tired. It is transformed because the space it travels through has changed. This is why older light becomes harder to see. Not because it fades into nothingness, but because it migrates out of the range our eyes evolved to detect. Human vision occupies a very narrow slice of the electromagnetic spectrum. It is tuned to the light emitted by a sun-like star, reflected off nearby objects, within Earth's atmosphere. That narrow tuning works beautifully for survival. It is almost useless for deep cosmology. The early universe does not speak in visible light. The first stars and galaxies emitted light that was often bluer and more energetic than the light we see around us today. But after billions of years of travel through expanding space, that same light arrives, stretched, cooled, and shifted far into the infrared. This has an important implication that is sometimes overlooked. The early universe is not dim because it was weak. It is dim because its light has been diluted across time and space, stretched thin by expansion, and shifted into wavelengths that ordinary telescopes cannot see. Trying to observe the early universe with visible light is like trying to hear a distant foghorn using ears tuned only for birdsong. The sound is still there. It simply exists in a register you are not equipped to perceive. This is why infrared astronomy is not optional for deep-time observation. It is mandatory. If a telescope cannot see infrared light, it will miss the most ancient signals the universe has to offer. No amount of image processing can recover information that was never detected in the first place. Sensitivity alone is not enough. The wavelength range must match the message being sent. This realization reshaped telescope design in fundamental ways. Earlier observatories achieved extraordinary things using visible and near-infrared light. They revealed galaxies in astonishing detail and pushed observation deep into cosmic history. But as astronomers pushed further back, they encountered a wall, not a sharp boundary, but a growing loss of information. The oldest galaxies appeared faint, red, and incomplete. Their light had shifted beyond reach. The universe was effectively whispering in infrared. To listen properly, astronomers needed instruments built from the ground up with that reality in mind. Mirrors optimized not just for sharpness, but for collecting faint stretched light. Detectors cooled to extreme temperatures so their own heat would not overwhelm ancient signals. Locations far from Earth's warmth and interference. This design logic is not about prestige or ambition. It is about alignment. The universe expands, light stretches, wavelengths shift. Therefore, telescopes must adapt. This chain of reasoning leads directly to the James Webb Space Telescope. Its emphasis on infrared observation is not a technological flourish. It is a direct response to cosmic expansion itself. James Webb was designed to operate where the early universe now resides in wavelength space. It does not chase visible photons that no longer exist. It listens for infrared ones that have been traveling since the universe was young. This is also why the telescope's images often look unfamiliar. Colors appear warm, golden, deep red. Structures feel softer, more diffuse. This is not artistic choice. It is translation. Data collected in infrared wavelengths is mapped into colors humans can see, preserving relationships while acknowledging that the original light lies beyond vision. Understanding redshift makes this translation easier to appreciate. The colors represent history. The redness is not decorative, it is diagnostic. It tells astronomers how far the light has traveled and how much the universe has expanded since it began its journey. Redshift becomes a kind of cosmic timestamp. By measuring how stretched the light is, astronomers infer how much space has expanded. From that, they estimate how long the light has been travelling. Distance, expansion, and time become intertwined. This is why expansion is not a background detail in cosmology. It is the central mechanism that shapes what can be seen at all. Without expansion, the universe would look radically different. Light would retain its original wavelengths. The early universe might appear brighter and bluer, but without expansion, the universe itself would not resemble anything observed today. structure formation, galaxy evolution, and cosmic history would all unfold differently. Expansion is not an inconvenience layered onto an otherwise static cosmos. It is the process that gives the universe its evolving character. And it is gentle. Despite the scale involved, expansion does not tear galaxies apart or stretch solar systems. Gravity dominates at small scales. Expansion becomes noticeable only across vast cosmic distances where gravity weakens and space itself takes the lead. This gentleness is easy to miss, but it is precisely what allows ancient light to survive its journey. Photons are not ripped apart. They are stretched smoothly, carried forward on the slow swelling of space. By the time they arrive, they are older, longer, cooler, and quieter. But they're still intact, still carrying information, still able to tell a story. That story cannot be heard without the right instruments, which is why understanding expansion and redshift is not an abstract exercise. It is the reason certain questions about the universe can be asked at all. It explains why seeing farther back requires listening at longer wavelengths, and it reveals why the deepest views of cosmic history must be infrared by necessity, not by choice. The universe expands, light stretches, and observation adapts, or it falls silent. Light comes in many forms, even though human eyes only recognize a small fraction of them. What we call visible light occupies a narrow band, balanced neatly between shorter, more energetic waves and longer, gentler ones. Just beyond the red end of visible light lies infrared. Infrared light is not exotic or rare. It is everywhere. It is emitted by warm skin, cooling pavement, distant planets, forming stars, and the faint afterglow of the early universe itself. The only reason it feels unfamiliar is because human vision never evolved to see it. In physical terms, infrared light has longer wavelengths and lower energy than visible light. That does not make it weaker in any absolute sense. It simply means each wave carries its energy spread out over a greater distance. Where visible light arrives in quick, tightly packed oscillations, infrared light moves with a slower, more relaxed rhythm. This difference turns out to be essential for astronomy. As light travels across the expanding universe, its wavelength stretches. Energetic light gradually becomes less energetic, not because anything drains it away, but because the space it travels through grows. By the time light from the earlier stars and galaxies reaches Earth, it has often been shifted completely out of the visible range. What once shone blue or ultraviolet arrives warm and red, or deeper still, into infrared. This is why the early universe speaks infrared. The first generations of stars were massive, hot and short-lived. They burned brightly, emitting large amounts of high-energy light. But that light began its journey when the universe was small, dense, and young. Over billions of years, as space expanded, those wavelengths were stretched again and again. By the time they arrive here, they're no longer visible light at all. This transformation does not erase information. It changes the form in which that information arrives. And to receive it, telescopes must be designed to listen in the right part of the spectrum. There is another reason infrared light dominates the deep universe, and it has nothing to do with expansion. Everything with a temperature emits radiation. This is known as thermal radiation, and it applies universally. Hot objects emit more energetic light. Cooler objects emit gentler, longer wavelength light. A blazing star emits strongly invisible and ultraviolet. A warm planet glows in infrared. A cold cloud of gas barely above absolute zero emits in far infrared and radio wavelengths. The universe is old. On average, it is cold. As cosmic structures age and expand, their temperatures drop. The background glow of the universe itself now sits just a few degrees above absolute zero, radiating almost entirely in microwave wavelengths. Young stars and galaxies stand out against this background, but even they appear cooler once their light has been stretched across time. This means infrared telescopes are not only looking for stretched starlight, they're also naturally tuned to the temperatures that dominate much of the cosmos. Cold objects that are nearly invisible in visible light can shine brightly in infrared. Dust clouds, star-forming regions, and early galaxies often reveal their true structure only when observed at longer wavelengths. Dust plays a particularly important role here. Interstellar dust is made of tiny solid grains, composed of elements like carbon and silicon. These grains are extremely effective at blocking visible light. They scatter it, absorb it, and obscure whatever lies behind them. In visible images, dust lanes carve dark silhouettes across galaxies, hiding star-forming regions and distorting structure. But dust interacts very differently with infrared light. Longer wavelengths pass through dust more easily, slipping between grains rather than bouncing off them. Infrared light can penetrate regions that appear completely opaque in visible images, revealing stars and structures that would otherwise remain hidden. This ability transforms how astronomers see the universe. Star-forming regions that look like dark voids in visible light become rich, glowing landscapes in infrared. The dense cores of galaxies, often shrouded in dust, open up. Entire populations of stars emerge from what once looked like empty space. This is not a subtle improvement, it is a change in perspective. In the context of the early universe, dust becomes both an obstacle and a clue. Early galaxies rapidly enrich their environments with heavier elements, forming dust surprisingly quickly. That dust absorbed visible light and re-emitted it in infrared, further shifting the balance toward longer wavelengths. So even without cosmic expansion, infrared would still be essential. With expansion layered on top, it becomes unavoidable. This is where the limits of earlier telescopes come into focus. The Hubble Space Telescope revolutionized astronomy. It delivered images of breathtaking clarity and pushed observation deep into cosmic history. It revealed galaxies billions of light-years away and mapped the large-scale structure of the universe with unprecedented precision. But Hubble was designed primarily for visible and near-infrared light. That choice reflected the scientific priorities and technological realities of its time. As astronomers pushed toward earlier epochs, they began to encounter a barrier. The faintest, most distant galaxies appeared redder and harder to resolve. Their light was slipping out of Hubble's most sensitive range. The telescope could see hints, suggestions, and partial structures, but not the full picture. This was not a failure of Hubble, it was a consequence of physics. The universe had shifted its language. To go further back, astronomers needed to listen where the universe was now speaking most clearly. That meant longer wavelengths. That meant colder detectors. That meant designing an observatory around infrared from the very beginning, rather than treating it as an extension of visible light astronomy. This realization shaped a new generation of instruments. Infrared astronomy requires special care. Infrared detectors must be kept extremely cold, or they will be overwhelmed by their own heat. The telescope itself must avoid warming from the sun, Earth, and even its own electronics. Observing infrared light is less like taking a photograph and more like listening for a whisper in a quiet room. But the reward is access to a universe that would otherwise remain invisible. When astronomers look in infrared, They're not simply seeing farther, they're seeing differently. They're tuning into a wavelength range that carries the signatures of early star formation, hidden galactic cores, and ancient cosmic structures. Infrared becomes a bridge between eras. It connects the hot, energetic beginnings of stars and galaxies to their cooled, stretched present-day signals. It allows observation to keep pace with expansion, rather than falling behind it. Understanding this makes the design choices of modern space telescopes feel less like bold gambles and more like careful responses. The universe expands, light stretches, dust obscures, temperatures drop, therefore observation must shift. Infrared is not an upgrade, it is a translation. It is the language the early universe uses now after billions of years of travel, and any attempt to understand cosmic dawn without it would be like trying to read a story written in a script you refuse to learn. The universe has already chosen how it speaks. Astronomy simply listens. For many people, space astronomy is almost synonymous with the Hubble Space Telescope. For decades, it has shaped how the universe looks in the public imagination. Spiral galaxies suspended in darkness, nebulae glowing with intricate color, deep fields crowded with countless distant galaxies. Hubble did not just collect data, it changed expectations. Scientifically, its impact has been just as profound. Hubble helped refine the expansion rate of the universe, reveal the large-scale structure of galaxies, trace the life cycles of stars, and provided some of the clearest evidence for dark energy. It showed that the universe is not only vast but richly structured, even at enormous distances. But understanding how far back Hubble could see requires separating what it did exceptionally well from what physics quietly prevented it from doing. Hubble was designed primarily to observe visible light, with some ability to extend slightly into ultraviolet and near-infrared wavelengths. This made it extraordinarily powerful for studying stars and galaxies in a wide range of environments, especially those relatively close in cosmic terms. It could resolve fine details, separate tightly packed stars, and produce images of remarkable sharpness. When Hubble looked far into space, it could indeed detect galaxies that were billions of light-years away. Its famous deep field images demonstrated this dramatically. By staring at a tiny patch of sky for many days, Hubble revealed thousands of distant galaxies, each representing a different era of cosmic history. In that sense, Hubble could see very far back. But seeing something is not the same as seeing it clearly. The most distant galaxies Hubble detected often appeared as small reddish smudges. Their shapes were difficult to interpret. Their internal structure was largely unresolved. In many cases, astronomers could tell that a galaxy was there, but not much more than that. This was not because those galaxies were poorly formed or unusually faint by nature. It was because the light reaching Hubble had been stretched out of its most sensitive range. As galaxies become more distant, their light shifts toward longer wavelengths. The farther back the light originated, the more extreme this shift becomes. For galaxies formed during the universe's earliest periods, much of their light arrives deep in the infrared. Hubble could detect the reddest edge of this light, but only barely. It was like catching the last few notes of a song as it fades below hearing. Enough to know something is playing, but not enough to hear the melody. This limitation arises from the interplay of three factors: mirror size, sensitivity, and wavelength range. Mirror size determines how much light a telescope can collect. A larger mirror gathers more photons, which is essential when observing extremely faint objects. Hubble's mirror, at just over 2 meters across, was a marvel of engineering, but it set a finite ceiling on how much ancient light could be captured. Sensitivity determines how effectively detectors can register faint signals without being overwhelmed by noise. Hubble's instruments were extraordinarily sensitive for their time, but they still had limits imposed by detector technology and thermal background. Wavelength range determines which parts of the cosmic message can be heard at all. This is where the most fundamental constraint appeared. If light arrives outside the wavelengths a telescope is designed to detect, no amount of sensitivity or exposure time can recover it. These three factors do not act independently. They compound. As astronomers pushed Hubble toward earlier and earlier epochs, they encountered a narrowing window. The galaxies were fainter, their light was redder, and the signal increasingly slipped beyond Hubble's optimal range. Exposure times grew longer, uncertainty grew larger, and interpretation became more cautious. This gradual loss of clarity was not a surprise. It had been anticipated long before Hubble ever launched. Scientists understood that visible light astronomy would eventually run out of reach, not because of a lack of skill or effort, but because the universe itself shifts its signals as time passes. The early universe does not send its messages in the same wavelengths it once used. In this sense, Hubble did exactly what it was designed to do. It carried astronomy to the edge of what visible and near-infrared light could reveal. It mapped that boundary with remarkable precision, and that boundary became a guide. Rather than trying to push Hubble beyond its natural limits, astronomers used its results to define the requirements for a different kind of observatory. One optimized not for the universe as it looks nearby, but for how the earliest universe appears after billions of years of expansion. This is where the James Webb Space Telescope enters the story. James Webb was never intended to replace Hubble. The two telescopes were designed to answer different questions, operating in different parts of the spectrum, with different strengths. Hubble excels at sharp, visible light imaging and long-term monitoring of nearby and intermediate distance objects. James Webb was designed to extend vision into deeper time. Where Hubble strained at the red edge of its capabilities, James Webb was built to begin there. This was not a speculative gamble. It was a direct response to known scientific limits. Astronomers could already see where Hubble's reach ended. They could already estimate what wavelengths carried the information they were missing. The challenge was not deciding whether an infrared telescope was needed. It was deciding how far into infrared it must go, and how sensitive it needed to be to capture the faintest ancient light. James Webb's larger mirror, colder operating temperature, and infrared-focused instruments were all chosen to address these specific constraints. Each design decision traces back to a clear physical reason. Light from the earliest galaxies is faint, therefore the mirror must be large. Infrared signals are easily drowned out by heat. Therefore, the telescope must be extremely cold. Expansion stretches light into long wavelengths. Therefore, detectors must be tuned accordingly. Seen this way, James Webb is not a leap into the unknown. It is a careful continuation. Hubble showed what could be done with visible and near-infrared light. It revealed where clarity gave way to ambiguity. It provided the data that defined the next step. There's a quiet continuity in this progression. Science advances not by abandoning successful tools, but by understanding their boundaries. Hubble's limitations were not obstacles to be overcome blindly. They were signposts pointing towards deeper time. By recognizing those limits, astronomers did not diminish Hubble's legacy. They completed it. The universe does not yield its history all at once. It reveals itself in layers, each accessible only when observation aligns with physical reality. Earlier telescopes opened vast chapters of cosmic history. They also showed with remarkable honesty where the pages grew thin. James Webb was built to read further, not because earlier efforts failed, but because they succeeded well enough to show exactly what was missing. Seeing deep into the past is not just a matter of pointing a telescope at the sky and waiting. It requires building an instrument that respects how the universe actually behaves. Light is faint. Space is cold. Time stretches signals until they barely whisper. To listen properly, the telescope itself must become an exercise in restraint, patience, and precision. This is the philosophy behind the James Webb Space Telescope. From the beginning, it was clear that no single country or agency could realistically build such an instrument alone. The scientific ambition was too large, the engineering challenges too complex, and the timescale too long. Instead, the project became a collaboration between NASA, European Space Agency, and Canadian Space Agency. This international coordination was not symbolic. Each partner contributed essential components, expertise, and scientific leadership. Instruments, launch capability, detectors, and mission operations were divided deliberately, ensuring that the telescope reflected a shared global investment in understanding the early universe. The result is not just a machine, but a convergence of scientific priorities shaped by decades of prior discovery. At the heart of the telescope lies its most visually striking feature, the mirror. Mirror size matters enormously in astronomy, but not for the reason most people first imagine. Bigger mirrors do not primarily mean sharper images, they mean more light. Ancient light is scarce. Photons emitted billions of years ago arrive at Earth spread thin across a vastly expanded universe. By the time they reach a telescope, they are few in number, faint in energy, and easily lost in background noise. A larger mirror has more surface area to intercept those photons. It is less about magnification and more about gathering power. The larger the collecting area, the more ancient light can be accumulated over time, improving sensitivity and confidence in detection. James Webb's mirror spans more than 6 meters across, giving it over 6 times the light collecting area of Hubble. That difference is transformative. Objects that would require weeks of observation with a smaller mirror can be studied in far greater detail or even detected at all. But building a mirror that large introduces a practical problem. Rockets have finite size. A solid mirror 6 meters across simply cannot fit inside a launch vehicle. The solution was not to shrink ambition, but to rethink geometry. Instead of a single piece of glass, James Webb uses a segmented mirror made of 18 individual hexagonal segments. Together, they form a single reflective surface, carefully shaped and aligned to act as one. These segments had to be folded for launch, tucked compactly inside the rocket's fairing. After launch, they would deploy, unfold, and align themselves in space with astonishing precision. Each segment could be adjusted independently, allowing engineers to fine-tune the mirror's shape down to incredibly small tolerances. This deployment was not a dramatic flourish. It was a necessity imposed by physics and engineering. Folding allowed size without sacrificing launch constraints. Segmentation allowed control and correction once in space. There is a quiet elegance in this design. It mirrors the scientific goal itself. To see the early universe, light must be gathered patiently, piece by piece, and assembled into understanding. Mirror size alone, however, is not enough. Infrared astronomy brings a unique challenge. Everything warm emits infrared radiation. That includes stars, planets, people, and unfortunately telescopes. If the telescope itself is warm, it will glow brightly in infrared, overwhelming the faint cosmic signals it is trying to detect. It would be like trying to hear a whisper while standing next to a roaring fire. To avoid this, James Webb must be kept extraordinarily cold. Its instruments operate at temperatures only a few degrees above absolute zero. At these temperatures, thermal noise drops dramatically, allowing detectors to register faint infrared photons arriving from the early universe rather than the telescope's own heat. Achieving this cold environment required another bold design choice. Instead of orbiting close to Earth, James Webb operates far away, at a stable point where the gravitational pull of Earth and the Sun balance in a predictable way. From this location, the telescope can keep its sunshield permanently oriented to block heat and light from the Sun, Earth, and Moon. The sunshield itself is a marvel of purpose-driven engineering. Made of multiple layers of reflective material, it passively cools the telescope by allowing heat to radiate away while preventing new heat from reaching the instruments. No active refrigeration is required for most components. The universe itself becomes the cooling system. This is engineering in service of listening. Every aspect of the telescope's design flows from a single requirement: detect faint, stretched, ancient light without interference. Large mirror, infrared optimized detectors, extreme cooling, stable thermal environment, precise alignment. None of these features exist for their own sake. They are responses to the conditions imposed by deep time. The earliest luminous structures in the universe were not bright by modern standards. They were small, chaotic, and embedded in environments rich with gas and dust. Their light has travelled for billions of years, stretched and thinned by expansion. By the time it reaches us, it carries crucial information, but only just enough to be detectable. James Webb was built to meet that challenge directly. This is why it is misleading to think of the telescope as a leap of faith or a speculative gamble. The physics was already known. Astronomers understood how light behaves, how expansion stretches wavelengths, and where earlier instruments fell short. The telescope was not designed to chase surprises blindly, but to access a region of observation that physics clearly indicated existed. In that sense, James Webb is conservative in the best scientific way. It does not assume the universe will behave differently than expected. It assumes the universe will behave exactly as physics predicts, and builds an instrument capable of listening accordingly. The international nature of the project reinforces this mindset. Scientific consensus guided design choices. Trade-offs were debated carefully. Every gram of mass, every layer of shielding, every adjustment mechanism had to justify itself in terms of scientific return. And the scientific return was always defined by one question: how far back can observation realistically reach? Not how far back would be impressive, not how far back would sound dramatic, but how far back light itself allows. The telescope's engineering does not promise to reveal the beginning of everything. It does not claim to pierce all cosmic veils. Instead, it promises to approach the earliest luminous moments with clarity, patience, and honesty. This restraint is its strength. By building a telescope that accepts the universe's limits rather than fighting them, astronomers created an instrument capable of operating right at the boundary between what can be observed and what cannot. The deep past does not announce itself loudly. It arrives faintly, slowly, and in infrared. James Webb was built to notice. Collecting ancient light is only the first step. Once those faint photons reach the telescope, they must be interpreted. They must be translated from a dim glow into physical meaning. This is where James Webb's instruments quietly do their most important work. The James Webb Space Telescope does not simply take pictures, it measures light. Every observation is designed to answer questions about what that light is made of, where it came from, and what happened to it along the way. Among its most important tools are instruments such as the near-infrared camera, often called near-infrared cam, and the near-infrared spectrograph, often called near-infrared spec. Their names sound technical, but their roles are conceptually simple. One shows where light is, the other explains what that light contains. Near-infrared cam is responsible for imaging. It reveals structure. It shows galaxies as shapes rather than points, resolving faint smudges into clusters, arcs, and irregular forms. Through it, astronomers can see where ancient light is arriving from and how it is distributed across space. But images alone are not enough. A galaxy's shape can tell you something about its size and structure, but not much about its composition or history. To understand what a distant object is made of, how hot it is, or how fast it is moving, astronomers must look beyond brightness and shape. They must look inside the light itself. This is where spectroscopy enters. Spectroscopy is the practice of separating light into its component wavelengths. Instead of treating light as a single glow, it is spread out into a spectrum, revealing how much energy arrives at each wavelength. The result is not a picture in the usual sense, but a pattern. This pattern carries extraordinary information. Different atoms and molecules interact with light in specific ways. They absorb certain wavelengths and emit others. These interactions leave distinctive marks in the spectrum, often described as fingerprints. Hydrogen leaves one pattern, oxygen leaves another. Carbon, nitrogen, iron, and countless other elements each imprint their own signatures. By studying these patterns, astronomers can identify which elements are present in an object, even if it lies billions of light-years away. This is not guesswork. These spectral fingerprints are measured in laboratories on Earth and confirmed through decades of observation. The same hydrogen that glows in a laboratory plasma produces the same spectral pattern in a distant galaxy. Physics does not change with distance. Through instruments like near-infrared spec, James Webb can disperse ancient infrared light and read these fingerprints with remarkable sensitivity. A faint galaxy that appears as a soft glow in an image suddenly becomes a source of chemical information. From this, astronomers can learn what the earliest galaxies were made of. They can determine whether a galaxy contains only the simplest elements formed shortly after the universe began, or whether it has already been enriched by generations of stars producing heavier elements. This distinction matters deeply. It tells scientists how quickly stars formed, lived, and died in the early universe. Spectroscopy also reveals temperature. Hot objects emit light differently from cool ones. The overall shape of a spectrum carries information about how energetic the emitting source is. A population of massive hot stars produces a different spectral signature than a cooler, more mature stellar population. In this way, astronomers can infer whether an early galaxy is dominated by young, massive stars or contains a more diverse mix. They can estimate how actively stars are forming and how much energy is being released into the surrounding environment. Motion is encoded as well. When an object moves relative to the observer, the wavelength of its light shifts slightly. Light from an object moving away appears stretched toward longer wavelengths. Light from an object moving closer appears compressed toward shorter ones. This effect allows astronomers to measure how fast galaxies are receding due to cosmic expansion. For distant galaxies, this shift becomes a powerful clock. The amount of stretching in the spectrum reveals how much the universe has expanded since the light was emitted. From that, astronomers estimate how long the light has been travelling. Distance and age emerge not from direct measurement, but from reading the history written into the light itself. This is one of the most subtle and elegant aspects of astronomy. No ruler spans billions of light years. No stopwatch can be sent into the past. Instead, light arrives carrying its own record of the journey. James Webb's instruments are designed to read that record with care. This is especially important when dealing with the earliest galaxies. These objects are faint, small, and often irregular. Their light arrives weakly, sometimes just above the background noise of the universe. Turning that faint signal into reliable data requires extreme sensitivity and stability. By combining imaging from near-infrared CAM with spectroscopy from near-infrared SPEC, astronomers can identify a distant galaxy, isolate its light, and then analyze its spectrum. The image tells them where to look. The spectrum tells them what they are seeing. Together, these measurements transform vague shapes into physical systems. A galaxy stops being just a point of light and becomes a collection of stars, gas, dust, and motion. Its chemical makeup hints at how many generations of stars preceded it. Its temperature reveals how violently it is forming new stars. Its spectral shift places it at a specific moment in cosmic history. This is why James Webb's instruments are so central to its mission. They are not accessories, they are interpreters. The telescope does not simply look deeper than before, it understands more deeply. This distinction matters because early observations of the distant universe often involved ambiguity. A faint red object might be a very distant young galaxy, or it might be a closer, dust-obscured one. Without spectral information, the difference can be difficult to resolve. Spectroscopy cuts through that uncertainty. By identifying specific absorption and emission features, astronomers can distinguish between distance and dust, between youth and maturity. They can place objects accurately within cosmic time, rather than relying on appearance alone. This careful approach reflects a broader scientific philosophy. Claims about the early universe must be grounded in measurement, not impression. The further back observation reaches, the more cautious interpretation must become. James Webb's instruments were built with this caution in mind. They allow astronomers to test ideas rather than assume them, to measure rather than infer loosely, to confirm that what appears ancient truly is ancient. In doing so, the telescope turns observation into a dialogue. Light arrives from the past. Instruments separate it, analyze it, and translate it into information. Astronomers listen, compare, and revise their understanding. The universe does not offer simple answers. It offers data. By measuring ancient light rather than merely displaying it, James Webb ensures that the story of the early universe is told not as speculation, but as evidence. Each spectrum becomes a fragment of cosmic history, preserved not in stone or text, but in the structure of light itself. And once light can be read this way, distance and age stop being abstract concepts. They become measurable properties, encoded quietly in every photon that arrives. In everyday life, distance is something you can measure directly. You can pace it out, stretch a tape across it, or watch numbers tick upward on a dashboard. Even when distances grow large, the basic idea stays the same. You measure from here to there, and you trust the tool in your hand. Astronomy offers no such convenience. No ruler reaches into space. No probe has travelled billions of light years to mark a position and report back. Instead, astronomers infer distance indirectly, by reading clues carried by light itself. Distance is not measured so much as reconstructed. One of the most important of these clues is redshift. As light travels through an expanding universe, its wavelength stretches. The amount of stretching depends on how much the universe has expanded during the light's journey. The farther the light has travelled, the greater the expansion tends to be. By measuring how shifted the light's spectral features are, astronomers estimate how much cosmic expansion has occurred since the light was emitted. This does not give distance in the way a ruler would. It provides a relationship between expansion, time, and separation. From that relationship, distance can be inferred using well-tested models of cosmic expansion, developed through decades of observation and theory. Redshift alone, however, is not always enough. Brightness provides another crucial piece of information. Light spreads out as it travels. The farther it goes, the thinner it becomes. If astronomers know how bright an object truly is, and how bright it appears from Earth, they can estimate how far away it must be. This is the same logic used when judging the distance of a streetlight at night. A dim light could be weak, or it could be far away. To decide which, you need more context. In astronomy, that context comes from objects whose intrinsic brightness is well understood. These are known as standard candles. A standard candle is an object that produces a predictable amount of light. If you know how luminous it truly is, then its observed brightness immediately gives you an estimate of distance. The universe provides a few such reliable beacons, and among the most important are certain types of supernovae. When some stars reach the end of their lives, they explode in remarkably consistent ways. These explosions briefly outshine entire galaxies. Because their peak brightness follows a known pattern, astronomers can use them as cosmic mile markers. By comparing how bright a supernova appears to how bright it is expected to be, distance can be estimated with surprising precision, even across billions of light years. These measurements have played a central role in modern cosmology. They helped refine the expansion rate of the universe and reveal that cosmic expansion is accelerating. Organizations such as NASA and the European Space Agency have supported decades of supernova surveys precisely because of their value as distance indicators. Spectral features add yet another layer of information. Specific absorption and emission lines act like reference marks. Their positions reveal redshift. Their relative strengths hint at physical conditions. Together, they help confirm whether a faint object is truly distant or merely obscured by dust. Distance estimation rarely relies on a single method. Instead, astronomers build what is sometimes called a distance ladder. Nearby objects are measured using one technique. Those measurements calibrate another technique that works farther out. That in turn supports methods that reach even deeper into space. Each rung depends on the ones below it. This layered approach is powerful, but it is not perfect. Uncertainty accumulates as distance increases. Small errors at one stage propagate upward. Assumptions that are safe nearby become harder to test far away. As observations push deeper into cosmic history, uncertainty becomes unavoidable. Faint objects are harder to measure. Their light is noisier. Their spectral features are weaker. Models of their intrinsic brightness rely more heavily on assumptions about early star formation and galaxy evolution. Even the expansion history of the universe itself introduces uncertainty at extreme distances. Astronomers do not hide this uncertainty, they quantify it. Distances are reported with ranges, margins, and confidence levels. A galaxy might be placed at one distance plus or minus a certain amount. Its age might be estimated within a span of hundreds of millions of years. These ranges are not signs of weakness. They are expressions of honesty. There is a temptation, especially outside science, to seek absolute answers, a single number, a definitive statement. But the universe does not always cooperate. At great distances, precision gives way to probability. This is why the question of how far back we can see is never answered with the single sharp boundary. Instead, it is described as a gradual approach toward a limit, with increasing uncertainty as that limit is neared. And this uncertainty is not merely tolerated, it is informative. When observations fall just within expectations, confidence grows. When they fall outside, theories are tested. Uncertainty becomes a space where discovery can occur. This is particularly true for observations made by the James Webb Space Telescope. James Webb operates in regimes where light is extremely faint and heavily stretched. It observes objects that sit near the edge of detectability. In these regions, small differences in interpretation matter. A slight shift in estimated redshift can move a galaxy hundreds of millions of years closer to or farther from the beginning of cosmic history. Rather than avoiding this ambiguity, astronomers embrace it carefully. Multiple observations are combined. Different instruments cross-check results. Independent teams analyze the same data. Claims are revised, refined, and sometimes withdrawn as new evidence emerges. This process can feel slow, but it is precisely what allows confidence to build over time. The farther back observation reaches, the more important this caution becomes. Early galaxies are not just distant, they are different. Their stars, gas, and dust behave in ways that challenge models built from nearby examples. Using familiar assumptions too rigidly can lead to misinterpretation. Recognizing uncertainty protects against that. It also reshapes what it means to measure distance. Distance stops being a single value and becomes a range of possibilities constrained by evidence. Age becomes an interval rather than a date. Location becomes a probability distribution rather than a fixed point. This may sound abstract, but it reflects how the universe actually presents itself at extreme scales. Light arrives incomplete, information is limited, interpretation must remain flexible. James Webb pushes observation into a realm where these limitations are not flaws but features, where uncertainty itself becomes a source of insight. When a galaxy appears earlier than expected, the question is not immediately whether the measurement is wrong. It is whether existing models need adjustment. In this way, uncertainty becomes a guide. By measuring distance without rulers, astronomers accept that the universe does not reveal itself all at once or with perfect clarity. It offers hints, patterns, and ranges. It invites careful reading rather than instant conclusions. And as observation presses closer to the earliest luminous moments, this careful reading becomes the most valuable tool of all. The universe does not demand certainty. It rewards patience. For a long time, the earliest galaxies existed only in theory. Astronomers could describe them mathematically, simulate them on computers, and infer their properties indirectly, but they could not see them clearly. They were predictions waiting for confirmation. Those predictions were not arbitrary. They emerged from models of how structure forms in an expanding universe, governed by gravity, gas dynamics, and time. According to these models, the first galaxies were not grand spirals or smooth ellipses. They were small, irregular, and restless. They formed in a universe that was still finding its balance, where matter had only recently begun to clump together in meaningful ways. In the early universe, matter was distributed almost uniformly, with only tiny variations in density. Over time, gravity amplified those variations. Slightly denser regions attracted more matter, growing slowly at first, then more rapidly. This process did not produce neat structures right away. It produced knots, filaments, and uneven concentrations. The earliest galaxies emerged within these dense pockets. They were modest by modern standards. Many contained only a fraction of the stars found in galaxies like the Milky Way. Their shapes were irregular and constantly changing, shaped by frequent mergers and rapid star formation. Rather than rotating gracefully, they often appeared turbulent and fragmented. This chaos was expected. Early galaxies formed in an environment rich in primordial gas. This gas was mostly hydrogen and helium, the simplest elements forged in the universe's earliest moments. Heavier elements had not yet been produced in significant quantities because stars had only just begun to form and die. As a result, early galaxies were chemically simple but physically intense. Gas collapsed quickly, forming massive stars at high rates. These stars burned hot and fast, flooding their surroundings with radiation and stellar winds. Supernova explosions followed soon after, stirring the gas and reshaping the young galaxies repeatedly. Stability was not a priority. Growth was. Another key ingredient in these models is dark matter. Dark matter does not emit light and does not interact with radiation in familiar ways, but its gravitational influence is profound. It outweighs ordinary matter by a large margin and acts as the scaffolding upon which galaxies form. In the early universe, dark matter clumped first. Its gravitational pull drew gas into growing halos, creating the conditions needed for star formation. Without dark matter, galaxies would struggle to form at all. With it, structure could emerge efficiently even when the universe was young and diffuse. Importantly, this role of dark matter is not speculative decoration. It is grounded in multiple lines of evidence, from galaxy rotation curves to cosmic background measurements, supported by organizations like European Space Agency and NASA. In the context of early galaxies, dark matter provides a quiet but essential framework. Within these dark matter halos, gas cooled, condensed, and ignited stars. The earliest galaxies were therefore deeply connected to their dark matter environments. Their sizes, shapes, and growth histories were all influenced by the invisible mass surrounding them. This theoretical picture led astronomers to expect certain features in the earliest galaxies. They should be compact. They should appear clumpy rather than smooth. They should show signs of intense star formation. And they should evolve rapidly, merging with neighbors and growing over relatively short cosmic timescales. For years, these expectations could only be tested indirectly. Earlier telescopes could glimpse distant galaxies, but not with enough clarity to confirm their detailed structure. A faint reddish blur could be many things. Without precise measurements, it was difficult to tell whether astronomers were seeing genuinely primitive systems or more mature galaxies disguised by distance and dust. This is where observations from the James Webb Space Telescope become decisive. With its infrared sensitivity and large collecting area, James Webb can resolve early galaxies with far greater detail. Shapes that once appeared as indistinct smudges now show structure. Compact cores, multiple star-forming regions, and irregular outlines emerge from the noise. In many cases, these observations align strikingly well with theoretical expectations. Early galaxies do appear small and chaotic. Their light suggests rapid star formation and relatively simple chemical composition. Their structures hint at frequent interactions and mergers. At the same time, James Webb has introduced surprises. Some early galaxies appear brighter and more massive than models predicted at such early times. Their existence raises questions about how quickly stars and galaxies assembled after the universe's initial dark period. Did gas cool more efficiently than expected? Did star formation proceed faster under certain conditions? Or are some distances being revised as measurements improve? These questions are not signs of failure, they're signs of progress. When observation confirms theory, confidence grows. When it challenges expectations, understanding deepens. The goal is not to preserve models unchanged, but to refine them until they describe reality more accurately. What emerges from these observations is a picture of the early universe as busy and dynamic rather than orderly. Galaxies did not wait patiently to mature. They grew through collisions, bursts of star formation, and rapid transformation. Many of the structures seen today have their roots in this restless era. This is why astronomers speak of cosmic dawn not as a single moment, but as a period. There was no instant when the first galaxy suddenly appeared fully formed. Instead, there was a gradual transition. Small structures formed, stars ignited, light began to spread, galaxies assembled piece by piece, overlapping in time and space. James Webb's observations help map this transition. They show galaxies at different stages of early development, revealing a continuum rather than a sharp boundary. Some systems are just beginning to shine. Others are already evolving toward more complex forms. By observing many such galaxies, astronomers can begin to reconstruct the sequence of events that led from a dark universe to one filled with light. This approach shifts the focus away from dramatic firsts and towards sustained processes. The first galaxies were not isolated miracles. They were the outcome of physical laws acting consistently across space and time. Understanding their appearance helps anchor the broader story of cosmic history. It shows how complexity emerged from simplicity, how structure arose from near uniformity, and how light gradually took hold of the universe. As the earliest galaxies come into view, cosmic dawn reveals itself not as a flash, but as a slow sunrise. Before the first stars formed, the universe was dark in a very literal sense. Not empty, not inactive, but unlit. Matter existed as vast clouds of gas, slowly cooling and drifting under gravity's influence. There were no points of brilliance, no stellar furnaces, no sources of visible light to break the darkness. This long interval is often called the cosmic dark ages. Cosmic dawn marks the end of that darkness. It is the period when the very first stars ignited, switching on the universe's earliest sources of light. This was not a single moment, like a cosmic light switch being flipped. It was a gradual transition, spread across millions of years, as the first pockets of gas finally became dense enough to collapse and heat until nuclear reactions began. Those first stars were unlike anything commonly seen today. Modern stars, including the Sun, form from gas clouds that already contain a mix of elements. Carbon, oxygen, iron, and many others are present, because previous generations of stars lived and died before them. This chemical richness influences how gas cools, fragments, and settles into stars of various sizes. The earliest stars had no such inheritance. They formed from gas made almost entirely of hydrogen and helium, the simplest elements created shortly after the universe began. Without heavier elements to help radiate energy away, this gas behaved differently as it collapsed. It resisted breaking into small clumps. Instead, it tended to form much larger structures. As a result, the first stars are thought to have been enormous. Many models suggest that these early stars were tens or even hundreds of times more massive than the Sun. With so much mass packed into a single object, their cores burned intensely. Nuclear reactions proceeded at a furious rate. These stars shone brilliantly, emitting large amounts of energetic radiation. But this brilliance came at a cost. Massive stars live fast and die young. While a star like the Sun can shine steadily for billions of years, the first stars likely exhausted their fuel in just a few million years. In cosmic terms, they barely had time to exist before collapsing or exploding. This fleeting nature is one reason they are so difficult to observe directly. By the time their light reaches us, the stars themselves are long gone. Even when they were alive, they were embedded within dense clouds of gas and dust, surrounded by forming galaxies and rapidly changing environments. Their individual signals are faint, scattered, and blended together. For telescopes, spotting a single first-generation star across billions of light-years is extraordinarily unlikely. But absence of direct sight does not mean absence of evidence. The influence of these first stars is written all over the early universe. One of the most important clues comes from ionized gas. The intense radiation produced by massive early stars was energetic enough to strip electrons from surrounding hydrogen atoms. This process transformed neutral gas into ionized gas, changing how it interacted with light. Large regions of the universe began to glow faintly and behave differently as radiation from early stars spread outward. This transformation left signatures that astronomers can detect indirectly, even if the stars themselves remain unseen. Another lasting imprint comes from chemical enrichment. The first stars were responsible for creating the universe's first heavy elements. When they ended their lives, often in powerful supernova explosions, they scattered newly forged elements into surrounding space. Carbon, oxygen, and other heavier atoms were released into the cosmic environment for the first time. This enrichment changed everything. Gas clouds containing even small amounts of heavier elements could cool more efficiently. They fragmented more easily. This allowed later generations of stars to form with a wider range of masses, including smaller, longer-lived stars like the Sun. In this way, the first stars reshaped the rules of star formation itself. Astronomers detect this legacy by studying the composition of early galaxies. Spectral measurements reveal the presence or absence of heavy elements. A galaxy with extremely low metallicity, meaning very few elements heavier than hydrogen and helium, points toward recent formation and limited stellar history. A slightly enriched galaxy suggests that earlier stars have already lived and died there. Through observations supported by organizations such as NASA and the European Space Agency, astronomers piece together this chemical timeline, using galaxies as archaeological sites. There's also evidence in the way early galaxies shine. Even if individual first stars cannot be isolated, their collective light can influence the overall glow of a galaxy. A population dominated by massive short-lived stars produces a distinctive spectral signature, rich in energetic radiation. By studying the integrated light from early galaxies, astronomers infer the types of stars likely present. In this way, the first stars announce themselves indirectly, through their effects rather than their appearance. Cosmic dawn, then, is not just about stars turning on. It is about the universe becoming chemically and radiatively active for the first time. Light began to travel freely across greater distances. Gas changed state. Structure grew more complex. Perhaps most importantly, the universe's transparency began to change. Before the first stars, much of the universe was opaque to certain wavelengths of light. Neutral hydrogen readily absorbed energetic radiation, preventing light from traveling far. As stars formed and ionized their surroundings, this opacity diminished. Regions of space became more transparent. Light could propagate more easily. Information could travel farther. Star formation did not merely add light sources, it altered the medium through which light moved. This gradual clearing of cosmic fog transformed the universe from a dark, closed environment into one increasingly open to observation. The influence of countless early stars overlapped, creating vast regions where light could pass with less resistance. This process was uneven and extended. Some regions lit up early, others lagged behind. Cosmic dawn unfolded patch by patch rather than all at once. Understanding this helps clarify why the first stars are better thought of as a population than as individuals. Their collective impact mattered far more than any single star's life. It also explains why modern telescopes focus on detecting the consequences of early star formation rather than the stars themselves. Ionized regions, chemical signatures, and galaxy-wide radiation patterns all provide reliable evidence, even when direct detection remains out of reach. There is a quiet elegance in this indirect approach. Rather than demanding to see the first stars directly, astronomers listen for the echoes they left behind. They read the changes written into gas, light, and composition. They reconstruct events that happened billions of years ago from subtle traces still visible today. Cosmic dawn in this sense is not just a moment in time, it is a transformation of the universe's character. Darkness gave way to structure, simplicity gave way to complexity, isolation gave way to interaction. And as star formation spread, it set the stage for an even larger change. By altering the transparency of space itself, the first stars prepared the universe for a new phase, one in which light could travel farther, structures could grow larger, and observation itself became possible across cosmic distances. As the first stars ignited and galaxies began to take shape, the universe entered a period of profound transformation. Light was no longer confined to isolated pockets. It began to change the very medium through which it travelled. This transformation is known as rionization, and it represents one of the most important transitions in cosmic history. To understand rionization, it helps to start with hydrogen. Hydrogen is the simplest and most abundant element in the universe. For a long time after the universe cooled from its earliest hot state, hydrogen existed mostly in a neutral form. Each atom held onto its electron, forming a gas that was widespread, cool, and relatively opaque to certain kinds of light. This neutral hydrogen shaped the early universe in subtle but powerful ways. It absorbed energetic radiation easily, preventing light from travelling freely over large distances. Even when the first stars formed, their light initially struggled to escape their immediate surroundings. Space itself acted like a fog, limiting visibility. Rayonization marks the period when this fog began to lift. As more stars formed, they produced increasing amounts of energetic light. This light had enough energy to knock electrons free from hydrogen atoms, turning neutral hydrogen into ionized hydrogen. Once ionized, hydrogen interacts with light very differently. It becomes far more transparent to energetic radiation. Over time, regions of ionized gas expanded outward from early stars and galaxies. These regions grew, overlapped, and eventually filled most of intergalactic space. The universe transitioned from being largely neutral to largely ionized. This was not an instantaneous event. Reionization unfolded gradually, unevenly, and locally. Some regions lit up early, dominated by clusters of young galaxies. Other regions remained neutral for longer, shielded by distance or lower star formation activity. The process likely spanned hundreds of millions of years. During this time, the universe changed its behavior. As ionized regions expanded, light could travel farther without being absorbed. Visibility increased. Galaxies became easier to observe across large distances. Radiation began to influence gas dynamics on larger scales, heating intergalactic material and altering how matter collapsed into new structures. Rionization mattered not just for what could be seen, but for what could form. Ionized gas behaves differently from neutral gas. It resists gravitational collapse more strongly, affecting how small galaxies grow. In some regions, reionization may have suppressed the formation of the smallest galaxies by heating their gas and preventing it from settling into stars. In other regions, it may have regulated star formation, shaping the balance between rapid growth and long-term stability. In this way, reionization helped sculpt the population of galaxies that followed. It acted as a kind of environmental filter, favoring certain structures and altering the fate of others. Understanding when and how reionization occurred is therefore essential for understanding galaxy evolution as a whole. But how can astronomers study a process that happened so long ago, across such vast distances? They do it by looking for the fingerprints reionization left behind. One of the most important tools in this search is spectroscopy. By examining the detailed structure of light from distant galaxies, astronomers can detect subtle signs of interaction between that light and surrounding hydrogen. Certain spectral features become weakened or altered depending on whether the intergalactic medium is neutral or ionized. When light passes through neutral hydrogen, specific wavelengths are absorbed more strongly. When hydrogen is ionized, those absorptions diminish. By measuring how these features change with distance and time, astronomers infer the state of hydrogen along the light's path. This is where the James Webb Space Telescope plays a crucial role. James Webb's sensitivity to infrared light allows it to observe galaxies from the era when reionization was underway. The spectral features associated with hydrogen absorption, originally emitted in energetic wavelengths, arrive stretched into the infrared. Webb is designed to detect them precisely. By observing many galaxies at different distances, astronomers can map how the transparency of the universe changed over time. They can estimate when ionized regions became common and when neutral hydrogen finally retreated. This approach turns reionization into a measurable process rather than a vague concept. Data from James Webb complements earlier measurements from other observatories, including studies of the cosmic microwave background, supported by organizations such as NASA and European Space Agency. Together, these observations help constrain the timing and duration of reionization. What emerges is a picture of the universe crossing a threshold. Before reionization, the universe was relatively simple. Matter was mostly neutral. Light traveled short distances before being absorbed. Structures were small and isolated. After reionization, complexity increased. Light propagated more freely. Galaxies interacted across larger scales. Radiation influenced gas far beyond individual star-forming regions. This transition reshaped the cosmic environment. It also reshaped what could be observed. As the universe became more transparent, the reach of observation extended naturally. Light from increasingly distant sources could make its way to observers without being erased along the journey. The observable universe expanded, not because space grew larger, but because it became more readable. This connection between reionization and observation is subtle but profound. The ability to see far back in time depends not only on telescope sensitivity, but on the state of the universe itself. Reionization made deep observation possible by clearing pathways for light. In this sense, the universe cooperated with astronomy, slowly opening itself to inspection. Reionization also marks a philosophical shift in cosmic history. It represents the moment when light stopped being a local phenomenon and became a global one. Individual stars no longer illuminated only their immediate surroundings. Their combined influence altered the universe at large. The early universe moved from isolation toward interconnection. Understanding this era helps place limits on how far observation can ultimately reach. Before reionization, light struggled to travel far. Beyond a certain point, information simply could not propagate efficiently. These limits are not imposed by technology. They are written into cosmic history. James Webb's observations approach this boundary carefully. They explore a time when the universe was transitioning from opacity to transparency, from simplicity to layered structure. In doing so, they bring astronomers closer to the earliest possible light that can still be observed directly. Not to the beginning itself, but to the edge where observation becomes feasible. Reionization, then, is not just a chapter in cosmic history. It is a gateway. It marks the moment when the universe became visible on the largest scales and when light began to travel far enough for deep-time observation to exist at all. Beyond it lies darkness, not because nothing existed, but because light could not yet carry the story forward. As observation reaches farther back in time, it eventually encounters a boundary that cannot be negotiated. Not a blur that might sharpen with better instruments, and not a gap waiting for future technology to fill in, but a genuine limit set by the universe itself. Beyond a certain point, there are no stars to observe. There are no galaxies either, no glowing structures, no concentrated sources of light at all. This boundary is not defined by distance alone, but by history. It marks a time before the universe had learned how to shine. This period is known as the Cosmic Dark Ages, and the name is more literal than dramatic. After the universe cooled enough for atoms to form, matter existed primarily as neutral hydrogen and helium gas. The universe was filled with material, structured by gravity and shaped by subtle density variations. But it was dark. Not empty, not inactive, simply unlit. There were no stars yet to ignite nuclear reactions, no galaxies to organize light into visible forms. In this era, there was nothing emitting starlight for a telescope to collect. This absence is not a mystery in the sense of missing knowledge. It is a predictable consequence of cosmic evolution. Stars require time to form. Gas must cool, collapse, and reach sufficient density. Gravity must work patiently before the first points of light can appear. The cosmic dark ages are therefore not an unknown chapter. They are a known silence. From an observational perspective, this silence matters deeply. Telescopes detect light. They cannot detect what does not emit. No matter how sensitive an instrument becomes, it cannot collect photons that were never produced. This is the hard observational limit. The universe does not offer an infinite archive of visible history. It offers a finite window, defined by the moment the first luminous objects appeared. Everything before that moment exists beyond direct observation. Understanding this helps clarify what it means to ask how far back a telescope can see. The answer is not simply a matter of distance, sensitivity, or engineering ambition. It is determined by when the universe began producing light that could travel freely across space. The James Webb Space Telescope was designed to approach this boundary as closely as physics allows. By detecting faint infrared light from the earliest galaxies and star-forming regions, it can observe conditions just after the first stars ignited. It can study the early stages of cosmic dawn in detail, mapping how light began to spread through space, but it cannot see before that. There is no switch to flip, no setting to adjust that would allow James Webb to peer into a universe with no stars. This is not a shortcoming of the telescope. It is a reflection of reality. Sometimes limits are framed as challenges waiting to be overcome. In this case, the limit is the phenomenon being studied. The absence of light is itself part of the universe's story. The cosmic dark ages are observable in an indirect way. Their presence is inferred through what follows them. The timing of star formation, the state of gas, and the conditions required for the first luminous structures all point back to a period of darkness that preceded them. Astronomers can model this era with confidence because it follows logically from known physics. Gravity behaves predictably. Gas dynamics are well understood. The absence of stars is not an assumption, but a necessary stage. This distinction is important. The Dark Ages are not mysterious because they are unknown. They are quiet because nothing was shining yet. James Webb's observations press up against the end of this silence. They explore the moment when the universe transitions from darkness to light, when the first stars begin to alter their surroundings, and when observation becomes possible at all. Beyond that transition lies a different kind of boundary. Even before stars formed, the universe was not completely opaque. There was radiation present, but it was trapped in a dense, hot environment. As the universe expanded and cooled, it reached a point where light could finally travel freely. This moment left behind a relic signal that still fills the universe today. This signal marks the final theoretical boundary of direct observation. Before this point, the universe was too dense and too energetic for light to escape. Photons were constantly scattered by charged particles, unable to move freely over large distances. The universe was effectively opaque. When conditions changed, light was released all at once, filling space with a uniform glow. That glow has been travelling ever since, cooling and stretching as the universe expanded. This is known as the cosmic microwave background. It does not come from stars or galaxies. It comes from the universe itself, from a time long before any luminous structures existed. It represents the earliest light that can be observed directly. James Webb cannot observe this radiation. Its instruments are tuned to infrared wavelengths associated with stars and galaxies, not the much longer wavelengths of the cosmic microwave background. This separation is intentional. Different questions require different tools. The existence of this background radiation marks the ultimate observational horizon. Beyond it lies a universe that cannot be seen with light at all, not because it is hidden, but because it predates transparency itself. Understanding this layered set of limits brings clarity to the idea of seeing back in time. First comes the limit of star formation. Before stars, there is no starlight to collect. Then comes the limit of transparency. Before the release of the cosmic background radiation, light could not travel freely. Each boundary is imposed by physics, not by observational capability. Technology can approach these limits. It cannot erase them. This realization is not discouraging. It is grounding. It tells us that the universe is not withholding information arbitrarily. It is structured in such a way that certain eras are accessible to direct observation, and others are not. Knowing where those boundaries lie helps focus scientific effort where it can be most productive. James Webb's role is to explore the last luminous threshold, to observe the earliest stars and galaxies, to study how light first reshaped the universe, and to map the transition from darkness to complexity. Beyond that, astronomy relies on different kinds of evidence. Theory, simulation, and indirect signals take over where direct light ends. This division of labour is a strength rather than a weakness. It allows each tool to be used where it works best. The cosmic dark ages remain dark not because they are hidden, but because they were never illuminated. The cosmic microwave background remains the oldest light because it marks the moment illumination became possible. Together, these boundaries define the edge of the observable universe in time. James Webb stands at that edge, listening carefully to the faintest echoes of the first stars. It does not promise to reveal everything. It promises to show us exactly how far light itself allows us to look, and in doing so, it reminds us that some limits are not obstacles to overcome, but features that give the universe its shape. If there is a single boundary that defines how far vision can reach into the past, it is marked by a faint glow that fills the entire universe. This glow is not produced by stars or galaxies. It does not come from any specific place. It is the leftover light from a time when the universe itself first became visible. This light is known as the cosmic microwave background. It is relic radiation, released when the universe was very young, long before the first stars ignited, and long before galaxies took shape. At that time, the universe was hot, dense, and filled with charged particles. Light existed, but it could not travel freely. Photons were constantly scattered by electrons, trapped in a dense cosmic fog. In this early state, the universe was opaque. As expansion continued, the universe cooled. Eventually, it reached a point where electrons could bind to atomic nuclei, forming neutral atoms. When that happened, light was suddenly free to travel long distances without being scattered. The universe transitioned from opaque to transparent. The moment of that transition released a vast flood of light in every direction. That light has been travelling ever since. Over billions of years, as the universe expanded, the wavelengths of that radiation stretched dramatically. What began as energetic light has cooled into a gentle microwave glow, now just a few degrees above absolute zero. It fills all of space uniformly, arriving from every direction with remarkable consistency. This is the oldest light that can ever be observed directly. It does not come from stars because stars did not yet exist. It does not come from galaxies because galaxies had not yet formed. It comes from the universe itself, from a moment when conditions finally allowed light to escape and carry information forward. This makes the cosmic microwave background unique. It is not an object. It is a snapshot of a time. By studying this radiation, astronomers gain insight into the universe's earlier structure, composition, and geometry. Tiny variations in its temperature reveal subtle density differences that later grew into galaxies and clusters. Its uniformity confirms large-scale properties of cosmic expansion. Observations of this background, supported by organizations such as NASA and European Space Agency, have shaped modern cosmology profoundly. They help constrain the age of the universe, the amount of ordinary and dark matter, and the overall shape of space-time. But despite its importance, this ancient light sits firmly outside the reach of the James Webb Space Telescope. This is not an oversight or limitation in design, it is intentional. James Webb is optimized to observe infrared light associated with stars and galaxies. The cosmic microwave background exists at much longer wavelengths, far beyond infrared. Detecting it requires instruments sensitive to microwaves, not the near and mid-infrared wavelengths Webb was built to measure. There is also a temperature difference to consider. James Webb operates at extremely low temperatures to avoid overwhelming faint infrared signals. Even so, the cosmic microwave background is colder still, emitting radiation at wavelengths that require a different observational approach altogether. Instruments designed to study it are tuned to its specific characteristics, trading spatial resolution for sensitivity to long wavelength radiation. In other words, different questions demand different tools. James Webb listens for the earlier stars and galaxies. Microwave observatories listen for the universe's first released light. Neither replaces the other. Together they define the full observable timeline. This separation highlights a profound truth about observation. There is an ultimate limit to what can be seen with light. Beyond the cosmic microwave background lies a universe that cannot be observed directly using photons. Before the release of this radiation, light could not travel freely. Information was trapped, scattered, and unable to propagate over large distances. No telescope, no matter how advanced, can see before that moment using light alone. This is not a failure of imagination or technology. It is a boundary imposed by the universe's own history. Understanding this boundary reframes how the question of seeing back in time should be understood. There is no endless regress of visibility. There is a beginning to what light can show, and that beginning is marked not by stars but by transparency. This realization can feel limiting at first. It places a firm horizon on direct observation. It tells us that some chapters of cosmic history will never be illuminated in the conventional sense. But it also brings clarity. Science advances most effectively when it understands its limits. Knowing where observation must stop allows theory, simulation, and indirect evidence to take over responsibly. It prevents overreach. It encourages humility. The cosmic microwave background does not represent a disappointment. It represents a triumph. It is astonishing that any signal from such an early time can still be detected at all. That the universe preserved this faint glow for billions of years, carrying it intact across expanding space, is remarkable. It provides a reference point, a baseline against which all later structure can be measured. James Webb operates just on the luminous side of this boundary. It studies the universe after light sources emerged, after stars began to shine, and after complexity took root. It cannot cross into the earlier opaque era, not because it falls short, but because that era lies beyond what light itself can reveal. This distinction matters. It reminds us that astronomy is not about unlimited access. It is about careful listening within the constraints nature provides. Each instrument occupies a specific place along the observable timeline, contributing a piece to a much larger picture. The cosmic microwave background marks the earliest page that can be read directly. Everything before it must be inferred through other means. Everything after it unfolds through stars, galaxies, and evolving structure. Seeing this boundary clearly is not a loss. It is an act of understanding. It grounds curiosity in reality. It aligns expectation with physics, and it highlights the quiet elegance of a universe that allows itself to be read, but only up to the point where light itself can carry the story forward. When astronomers look deep into the universe, they're never looking at data in isolation. Every faint galaxy, every stretched spectrum, every subtle glow arrives already framed by expectation. Not expectation in the sense of wishful thinking, but in the form of theory. Theoretical cosmology provides the context that makes distant observation intelligible at all. Without theory, a faint red smudge is just a smudge. With theory, it becomes a candidate galaxy forming at a particular stage of cosmic history under specific physical conditions, shaped by gravity, gas, and expansion. Theory does not replace observation. It gives observation a language. At the larger scales, cosmology relies on a set of well-tested physical principles. Gravity behaves predictably. Gas follows known thermodynamic rules. Light interacts with matter in measurable ways. Expansion stretches space uniformly on average. These principles are not invented for convenience. They're grounded in laboratory physics, local measurements, and decades of astronomical observation. The challenge comes when these principles are applied to conditions that no longer exist nearby. The early universe was hotter, denser, and simpler in composition. Stars formed differently. Galaxies assembled more rapidly. Interactions were more frequent. When astronomers observe faint objects from this era, they are seeing systems that do not have close modern equivalents. This is where theoretical models become essential. Models allow scientists to explore how known physics behaves under early cosmic conditions. They provide predictions for what early galaxies should look like, how fast stars should form, how gas should cool, and how structures should grow over time. These predictions are not precise blueprints. They are ranges of behavior shaped by assumptions and constrained by evidence. One of the most powerful tools for building these models is computer simulation. Modern cosmological simulations follow the evolution of matter from the early universe to the present day. They begin with initial conditions informed by observations of the cosmic microwave background, then allow gravity, gas dynamics, radiation, and expansion to operate over billions of years. The result is not a single universe, but many possible universes. Each simulation explores slightly different assumptions: how efficiently gas cools, how strongly stars influence their surroundings, how quickly structures merge. By comparing the outcomes to real observations, astronomers learn which assumptions are most consistent with reality. These simulations are computationally demanding, often running on powerful supercomputers supported by research institutions and space agencies such as NASA and the European Space Agency. But their value lies not in visual appeal, but in their explanatory power. They help bridge the gap between physical law and observed structure. Importantly, theory does not sit above observation, issuing instructions. Nor does observation simply validate theory in a one-way process. The relationship is iterative. Observations inform models. Models generate predictions. New observations test those predictions. Discrepancies lead to revision. Agreement builds confidence. This cycle repeats continuously. In this sense, theory and observation are partners. When the James Webb Space Telescope observes a galaxy that appears brighter, more massive, or more chemically evolved than expected at a given time, the response is not to force the observation to fit the model. The response is to ask whether the model needs adjustment. Perhaps star formation was more efficient in certain environments. Perhaps gas cooled faster than assumed. Perhaps mergers occurred earlier or more frequently. Or perhaps the interpretation of distance needs refinement. Each possibility is examined carefully. This is one of the quiet strengths of scientific interpretation. Models are not treated as beliefs to be defended. They are tools to be improved. Seeing further back in time intensifies this process. At closer distances, models are constrained by abundant data. Nearby galaxies can be studied in detail. Star formation can be resolved region by region. Gas dynamics can be measured directly. Uncertainty is relatively limited. As observation reaches into the early universe, data becomes sparser and noisier. Objects are fainter. Signals are weaker. Interpretation relies more heavily on models to fill in context. This does not weaken science. It changes how cautiously conclusions must be drawn. Theoretical guidance becomes more important, but also more tentative. James Webb was built with this dynamic in mind. Its purpose is not to confirm a single narrative about the early universe. It is to provide data rich enough to challenge narratives where needed. In some cases, Webb's observations align closely with expectations. Early galaxies appear small and irregular. Their chemical compositions reflect limited enrichment. Their star formation rates fit within predicted ranges. In other cases, Webb reveals tension. Galaxies appear surprisingly mature. Star formation seems to proceed faster than some models predicted. Structures look more developed at earlier times than expected. These tensions are not failures. They are opportunities. They indicate where understanding is incomplete, They highlight which physical processes may be missing or oversimplified in current models. They push theory to account for reality more accurately. This back and forth is the essence of cosmology. It is also why caution is essential. Early results are rarely final. Interpretations evolve as more data is collected, as simulations improve, and as different teams test the same observations using independent methods. Science advances not through instant certainty, but through sustained refinement. Understanding this helps frame what it means to see further back in time. It is not simply a matter of adding more years to a timeline. It is an expansion of the regime where theory and observation must work together under increasing uncertainty. The deeper the view, the more carefully interpretation must proceed. This does not diminish the value of observation. It elevates it. It places each new detection within a broader effort to understand how the universe behaves under extreme conditions. James Webb's role in this process is therefore subtle but powerful. It does not dictate conclusions. It supplies constraints. It forces models to confront reality at times, and scales they were never tested against before. In doing so, it reminds astronomers that knowledge is provisional. Theories are not monuments, they are scaffolding. They support understanding while it's being built, and they are modified as that understanding grows. Seeing further back means seeing into unfamiliar territory. It means encountering systems that do not behave exactly as expected. It means accepting that surprise is not an anomaly, but a sign that exploration is working. The universe does not owe us simplicity. It offers consistency, governed by physical law, but expressed through complex and evolving structures. Theory helps navigate this complexity. Observation anchors it, and interpretation emerges from their continuous dialogue. As James Webb extends vision deeper into cosmic history, that dialogue becomes richer, more challenging, and more revealing. Not because answers are being replaced, but because better questions are being learned. When new windows open onto the universe, surprises are almost guaranteed. Not because nature enjoys being dramatic, but because deeper observation reveals regimes that have never been tested before. The early universe is one of those regimes, and as data from the James Webb Space Telescope began to arrive, some of its first impressions raised eyebrows. Among the most discussed early findings were galaxies that appeared brighter, more massive or more structured than many models had anticipated at such early times. In some cases, these galaxies seemed to exist only a few 100 million years after the first stars were expected to form, yet they already showed signs of significant star formation and chemical enrichment. At first glance, this looked unsettling. If galaxies grew more quickly than expected, it might suggest that something fundamental about early cosmic evolution had been misunderstood. Perhaps stars formed more efficiently. Perhaps gas collapsed faster. Perhaps feedback processes behaved differently in the young universe. But in science, a surprising result is not the same thing as a revolutionary conclusion. The first step is always caution. Early observations are often based on small samples. Distance estimates rely on faint signals near the edge of detectability. Interpretation depends on models that may not yet fully account for early conditions. Any one of these factors can shift conclusions subtly but significantly. Astronomers know this well. When a galaxy appears unusually bright, several possibilities must be considered. It might truly be massive, or it might be experiencing a brief burst of star formation that temporarily boosts its brightness. Or it might be closer than initially estimated, with dust or unusual stellar populations affecting its appearance. Each option must be tested. Spectral measurements are revisited. Independent teams analyze the same data using different methods. Additional observations are scheduled to confirm or refine initial findings. Claims are phrased carefully, often with explicit uncertainty ranges. This restraint is deliberate. The history of astronomy contains many examples where early interpretations softened or changed as more data became available. What looks extraordinary at first often becomes understandable once context improves. This does not mean surprises are dismissed. It means they are handled responsibly. When multiple independent observations point in the same direction, confidence grows. If several galaxies show similar unexpected properties, and if those properties persist under careful analysis, then models must respond. And they do. Revising a model is not an admission of failure. It is a sign that the model is being used properly. Models are simplified representations of reality. They capture dominant processes while approximating others. When new data exposes a gap or oversimplification, adjusting the model improves its explanatory power. In the case of early galaxies, revisions might involve changing assumptions about how quickly gas cools, how efficiently stars form, or how strongly early stars influence their surroundings. They might refine how dark matter halos assemble, or how mergers proceed in dense early environments. Each adjustment strengthens understanding. It narrows uncertainty. It aligns theory more closely with observation. It clarifies which physical processes matter most under extreme conditions. This iterative refinement is central to how science progresses. Patience plays a crucial role here. Astronomical data does not arrive all at once. Observations take time. Analysis takes longer. Confirmation takes longer still. The urge to declare immediate conclusions must be resisted in favor of steady accumulation of evidence. Replication is equally important. A result seen once is interesting. A result seen repeatedly by different instruments and teams becomes meaningful. This is why agencies such as NASA and the European Space Agency emphasize long-term observation programs and open data access. Independent scrutiny is not a threat, it is a safeguard. This approach can appear slow from the outside, but it is precisely what allows confidence to grow. Over time, the early surprises revealed by James Webb have begun to settle into a more nuanced picture. Some galaxies do appear to form stars rapidly. Some structures assemble earlier than certain models predicted. But these findings do not overturn cosmology. They refine it. They suggest that the early universe may have been more efficient at building structure under certain conditions. They highlight where physical processes interact in complex ways. They remind astronomers that extrapolating from the nearby universe has limits. Seeing further back does not simply extend a timeline, it exposes regimes where familiar intuition becomes less reliable. This is one of the most valuable outcomes of deep observation. Surprises act as signposts. They indicate where understanding is incomplete and where effort should be focused. They direct attention toward the physics that matters most in extreme environments. In this sense, surprise is not disruption. It is guidance. The broader implication is that extending observational reach does more than fill in gaps. It tests the foundations of understanding. It reveals where assumptions hold and where they need refinement. As James Webb continues to collect data, early interpretations will continue to evolve. Some initial surprises may fade as uncertainties shrink. Others may solidify into genuine revisions of how early cosmic history unfolded. Either outcome strengthens science. What matters is not whether expectations are confirmed, but whether reality is described more accurately. That goal requires time, care, and a willingness to let understanding change. The early universe is not obligated to match our expectations. It operates according to physical laws, not predictions. The task of science is to listen carefully, interpret cautiously, and revise honestly. In doing so, surprises become part of the process rather than obstacles to it. They remind us that extending our reach into deep time is not about finding comfort in familiarity, but about learning how the universe actually behaves when it was young. And that lesson unfolds not in dramatic declarations, but in careful, patient progress. When people think of seeing in astronomy, they often imagine a camera pointed at the sky, quietly capturing what is already there. A distant galaxy shines, a detector records it, an image appears. It feels familiar, almost photographic. But astronomical seeing does not work that way. What appears on the screen at the end of the process is not a snapshot of a moment frozen in time. It is a reconstruction, a careful assembly built from measurements, corrections, and choices, all grounded in physics. This does not make astronomical images less real. It makes them more meaningful. Every astronomical observation begins with an interaction. Light leaves a source, travels across space, and is intercepted by an instrument. That instrument does not receive an image. It receives signals, counts, energies, arrival times, patterns of intensity recorded by detectors designed to be as quiet and stable as possible. From those signals, an image is constructed. This is true for every telescope, whether it operates in visible light, infrared, or beyond. It is especially true for instruments like the James Webb Space Telescope, which observes light far outside the range of human vision. Infrared light cannot be seen by human eyes. There is no natural color associated with it in perception. When James Webb measures infrared photons, it does not record red, gold, or blue in any literal sense. It records wavelengths and intensities. To make this information interpretable, astronomers map those measurements into colors we can see. This process is called color mapping, and it is one of the most misunderstood aspects of astronomical imagery. Colors in space images are not decorative. They are symbolic. Each color corresponds to a specific range of wavelengths or a particular physical property. Longer wavelengths might be mapped to red tones. Shorter infrared wavelengths might appear bluer. Different filters highlight different features. The goal is not to make the universe look pretty, although beauty often follows naturally. The goal is to make patterns visible. Color allows the eye to distinguish structures that would otherwise blend together. It helps separate regions of star formation from older stellar populations. It reveals temperature differences, chemical variations, and motion. In this sense, color is a translation tool. Signal processing plays a similar role. Raw astronomical data contains noise, background radiation, detector imperfections, cosmic rays, instrumental artifacts. These must be identified and corrected carefully. Calibration ensures that what is shown reflects the sky rather than the quirks of the instrument. This process involves comparing observations to known standards, adjusting for detector sensitivity, and removing signals that do not originate from the target. It is meticulous work, often invisible to the final viewer, but essential for accuracy. Far from distorting reality, these steps bring it into focus. Without calibration, images would be misleading. Brightness would be inconsistent. Colors would not correspond to physical properties. Structures might appear where none exist, or vanish where they should be visible. Transparency is central to this process. Astronomers document how images are produced, which filters were used, how data was combined, what processing steps were applied. This information is not hidden. It is shared openly, allowing other researchers to reproduce results or reinterpret data using different methods. This openness is a core scientific value, supported by institutions such as NASA and the European Space Agency. Images released to the public are accompanied by detailed explanations of how they were created and what they represent. Understanding this helps clarify an important point. Astronomical images are not illustrations. They are visualizations of measured data. They condense vast amounts of information into a form the human brain can grasp intuitively. They trade rawness for clarity. In doing so, they preserve accuracy while enhancing understanding. This is why two images of the same object can look different and still both be correct. One image might emphasize dust structure, another might highlight star-forming regions, a third might focus on temperature or motion. Each uses the same underlying data, but maps it differently to answer a different question. This flexibility is a strength, not a flaw. It allows astronomers to explore complex systems from multiple angles, extracting meaning from signals that would otherwise remain abstract. Returning to the idea of seeing as a physical act, this process completes the cycle. Light interacts with matter at the source. It travels across space. It interacts with detectors. Signals are recorded. Data is processed. Images are constructed. Interpretation follows. At no point is seeing passive. Even the final image is an interaction between data and perception, shaped deliberately to reveal structure and meaning. This perspective also guards against misplaced skepticism. Sometimes, the fact that astronomical images are processed leads to claims that they are artificial or misleading. But this misunderstands the role of processing. Without it, the data would be unusable. Processing does not invent information, it organizes it. The choices involved are guided by physical understanding, not aesthetic preference. Colors are assigned consistently. Scales are chosen to reflect real differences. Noise is reduced, not erased. Features are enhanced, not fabricated. The aim is fidelity to the underlying measurements. Seeing this clearly allows appreciation without confusion. One can admire the beauty of an image while understanding that it is a translation, not a photograph in the everyday sense. It also reinforces a deeper truth about astronomy. We do not see the universe as it looks. We see it as it behaves. Light carries information about temperature, composition, motion, and history. Instruments measure that information. Images present it in a form that can be explored. In this way, astronomical seeing is closer to listening than looking. It is the careful interpretation of signals that arrive from far away and long ago. This understanding circles back to the opening idea that observation is an interaction, not a passive gaze. From the first photon intercepted to the final image displayed, every step reflects choices shaped by physics, instrumentation, and purpose. Seeing is an act of engagement with reality, constrained by limits and enriched by interpretation. James Webb exemplifies this approach. Its images do not show the early universe as it would appear to human eyes. They show it as it can be understood. They reveal structure, chemistry, and history encoded in light that has travelled for billions of years. Recognizing this does not distance us from the universe. It brings us closer. It replaces the illusion of direct vision with something more honest and more powerful. Acknowledgement that understanding requires translation, that clarity requires construction, that seeing at cosmic scales is an achievement rather than a given. And in that achievement, the universe becomes not less real, but more deeply known. When astronomers speak about the observable universe, it is tempting to imagine a kind of cosmic wall, a vast sphere surrounding everything we can see, beyond which nothing exists or nothing matters. But this picture is misleading. The observable universe is not a boundary, it is a horizon. A boundary implies an edge you could reach if you travelled far enough. A horizon is different. It is defined by perspective and limitation. It marks how far information has had time to reach us, not how far reality extends. The observable universe includes everything from which light has been able to arrive since the universe became transparent. That definition is rooted entirely in physics. It depends on the speed of light, the age of the universe, and the way space itself expands. Beyond this horizon, there may be more galaxies, more structure, perhaps far more than what is visible. But their light has not reached us yet, and in some cases, it never will. Expansion plays a crucial role here. As the universe expands, distances between faraway regions increase. Light emitted long ago continues to travel toward us, but space stretches beneath it. For regions sufficiently distant, expansion can outpace the ability of light to ever close the gap. This means that some parts of the universe are not merely unseen for now, they are permanently unobservable. No future telescope, no matter how sensitive, can receive light from regions beyond this cosmic horizon. It is not a matter of waiting longer or building better instruments. It is a consequence of how space-time evolves. This idea can feel unsettling at first. It suggests that reality extends beyond what can ever be observed, that there are places, perhaps entire regions of the universe, that exist without any possibility of direct contact. But this is not an error or a flaw in understanding. It is a feature of the universe itself. The observable universe is defined by causality. It includes everything that has been able to influence us since the beginning. Outside it lie regions that are causally disconnected, not because they are hidden, but because the structure of space-time prevents interaction. This distinction matters when considering the role of powerful observatories like the James Webb Space Telescope. James Webb dramatically improves our ability to see faint and distant objects. It allows astronomers to study galaxies closer to the beginning of cosmic history than ever before. It approaches the edge of the observable universe in time by detecting light from the earliest luminous structures. But it does not redefine the horizon itself. James Webb cannot make the observable universe larger. It cannot bring permanently unreachable regions into view. What it can do is reveal detail within the horizon that was previously invisible. It sharpens our understanding of what lies near the edge without moving the edge. This distinction helps clarify what progress in astronomy really means. Advancement is not about erasing limits. It is about approaching them honestly and understanding them more clearly. The horizon remains where physics places it, regardless of how powerful our instruments become. There is an important conceptual shift here. Instead of thinking of the observable universe as incomplete, it can be thought of as complete in a specific sense. It contains everything that can ever affect us through light, or other signals limited by the speed of information. Beyond it lies reality that exists independently of observation. This does not reduce the significance of the observable universe. It defines it. Within this horizon lies the entire causal history that led to stars, galaxies, planets, and eventually life. Everything that shaped our existence is contained within what can, in principle, be observed. Understanding that some regions are fundamentally unobservable does not diminish science, it sharpens it. Science is not the pursuit of total access, it is the pursuit of accurate description within known limits. Recognizing those limits prevents speculation from drifting into assertion. It grounds curiosity in physical reality. Astronomers are comfortable with this restraint. It is well understood that certain questions cannot be answered directly. What lies beyond the observable universe is one such question. It may be addressed indirectly through theory or inference, but it cannot be seen. This acceptance allows focus to remain on what can be learned reliably. James Webb's contribution fits neatly within this philosophy. By extending observation closer to the horizon in time, it fills in missing chapters of cosmic history without claiming to reveal the unreachable. It shows how structure emerged, how light spread, and how complexity developed within the observable domain. In doing so, it brings the horizon into sharper conceptual focus. The more clearly the edge is understood, the more meaningful what lies within it becomes. This perspective also encourages a quieter form of wonder. Instead of fixating on what cannot be seen, attention turns to the richness of what can. The observable universe is vast beyond everyday intuition. It contains billions of galaxies, each with billions of stars, unfolding across billions of years. That this entire expanse is accessible to observation at all is remarkable. The horizon is not a denial. It is an invitation to think carefully about scale, causality, and limitation. It reminds us that knowledge grows not by ignoring boundaries, but by mapping them precisely. As observation approaches its furthest reach, the task becomes less about discovery in the dramatic sense and more about synthesis. About understanding how all the pieces fit together within the space that can be known. This sets the stage for reflection rather than revelation. The true edge of the observable universe is not a cliff or a wall. It is a gentle fading, where signals become weaker, older, and eventually unreachable. It marks where history gives way to inference, and where observation hands off to theory. Standing at this edge does not provoke alarm. It encourages perspective. It shows that the universe is larger than what can be seen, and that seeing is only one way of knowing. By the time all the pieces are set side by side, the question of how far back James Webb really sees becomes clearer and quieter than it first appears. There is no single dramatic cutoff, no sharp line where vision suddenly fails. Instead, there is a layered set of limits, each grounded in physics, each telling a slightly different part of the story. The first limit is observational. Light must exist in order to be seen. Stars and galaxies must form before they can emit anything at all. James Webb looks back to a time when the universe had already begun to light itself, when the first luminous structures were emerging from darkness. It does not see the beginning of everything. It sees the beginning of light. This distinction matters. The origin of the universe and the earliest moments of cosmic history lie beyond direct observation by any telescope. They are inferred through theory, background radiation, and indirect evidence. Observation, by contrast, begins later, when light is free to travel and sources exist to produce it. James Webb occupies a precise position in this timeline. It observes the universe after the cosmic dark ages, during and after the formation of the first stars and galaxies. It captures light that has travelled for more than 13 billion years, stretched into infrared wavelengths by the expansion of space, thinned by distance, and preserved just long enough to be intercepted. That is an extraordinary reach, but it is not unlimited, and it was never intended to be. The physical limits discussed throughout this journey do not compete with one another. They reinforce each other. The finite speed of light ensures that distance and time are inseparable. Cosmic expansion stretches wavelengths, shifting early light into infrared. The formation of the first stars defines when luminous signals begin. The transparency of the universe determines how far those signals can travel. The observable horizon marks where causality itself draws a line. James Webb operates at the intersection of these constraints. Its large mirror gathers faint ancient photons. Its infrared instruments listen where early light now resides. Its extreme cooling prevents the telescope from overwhelming the signals it seeks. Its location in space minimizes interference. Every design choice traces back to a specific physical requirement. Seen this way, James Webb is not a machine designed to defeat limits. It is a machine designed to respect them. This is why it is so effective. By aligning with the universe as it is, rather than as we might wish it to be, the telescope reaches the furthest point observation reasonably allows. It sees not to the origin of time, but to the earliest chapters where light begins to write a visible record. That record is rich. James Webb reveals early galaxies assembling rapidly, stars forming under unfamiliar conditions, gas cooling and collapsing in environments unlike those nearby. It shows structure emerging sooner than expected in some cases, and behaving exactly as predicted in others. It provides data that confirms certain models, challenges others, and refines nearly all of them. In doing so, it clarifies another important distinction. Seeing further back does not automatically mean understanding more deeply. Observation provides information. Interpretation requires theory, simulation, and patience. The deeper the observation, the more carefully conclusions must be drawn. James Webb does not hand over answers fully formed, it supplies constraints. Astronomers use those constraints to test ideas about early star formation, galaxy growth, chemical enrichment, and the role of dark matter. When observations align with expectations, confidence increases. When they do not, understanding evolves. This is not a weakness of science, it is its strength. Limits in this context are not failures. They are features of reality that give structure to inquiry. Knowing where observation must stop allows effort to be focused where it can be most productive. It prevents confusion between what can be seen and what must be inferred. The universe is not obligated to be fully observable. Some regions lie beyond the cosmic horizon. Some eras precede transparency itself. Some processes leave no direct luminous trace. Acknowledging this does not diminish discovery. It sharpens it. James Webb's contribution is therefore best understood not as a promise of total access, but as an act of precision. It defines, with unprecedented clarity, how far back observation truly reaches. It marks the edge of the luminous universe with data rather than speculation. That edge is not the beginning. It is the point where stars first ignited, where galaxies began to assemble, and where light first became abundant enough to shape the universe on large scales. Everything before that remains part of cosmic history, but not part of direct visual observation. This layered understanding brings calm rather than disappointment. It shows that science progresses by mapping boundaries as carefully as it explores interiors. It reveals a universe that is generous with information, but not infinite in what it offers to sight. It invites curiosity tempered by realism. The further back James Webb looks, the more clearly this balance comes into view. Observation reaches astonishing distances. Theory extends further still. Together they form a coherent picture of a universe that can be known deeply, even if not completely. How far back does James Webb really see? Far enough to show when light took hold of the universe. Far enough to witness the transition from darkness to structure. Far enough to test the foundations of cosmology with real data rather than assumption. And then, precisely where light itself runs out, it stops. Not because science failed, but because it succeeded in reaching the boundary set by reality itself. That understanding does not close the story. It completes this part of it, gently, leaving space for reflection on what it means to explore a universe that reveals itself only where physics allows. From here, the task is no longer to push harder, but to listen more carefully to what has already arrived. At the end of this journey, what remains is not a dramatic revelation, but a clearer sense of where vision gently gives way to silence. The James Webb Space Telescope was never meant to erase the universe's limits. It was built to bring them into focus. By listening carefully to faint, ancient light, it has shown how far observation can truly reach, and just as importantly, where it must stop. It has clarified the boundary between what can be seen and what must be inferred. In doing so, it has made the universe feel larger, not smaller. Knowing how far back we can see does more than satisfy curiosity. It deepens understanding of everything beyond that point. When the edge of observation is mapped precisely, the regions beyond it gain context rather than mystery. The cosmic dark ages are no longer imagined as a hidden realm waiting to be uncovered. They are understood as a time before light existed to carry information. The earliest moments of the universe are not obscured by secrecy, but by physics. They belong to a different category of knowledge. This distinction matters. It reminds us that science does not advance by demanding access to everything. It advances by working carefully within the structure of reality. The universe reveals itself in layers, and each layer comes with conditions. Light must exist. Space must be transparent. Information must be able to travel. James Webb respects those conditions. Its power lies not in spectacle but in alignment. It listens where the universe still speaks. It gathers what arrives without claiming to reach what cannot. That restraint is not a limitation of imagination. It is an expression of understanding. Astronomy has always required patience. Light does not hurry. It travels at its speed, not ours. Signals arrive when they arrive, carrying histories that cannot be rushed. Observations take time. Interpretation takes longer. Confidence grows slowly through repetition, verification, and revision. James Webb embodies this pace. Its observations are not instant answers. They're carefully accumulated evidence. Each faint galaxy adds a piece to a broader picture. Each spectrum refines understanding by a small but meaningful amount. Over time, clarity emerges not from single discoveries, but from sustained attention. Precision plays an equally central role. At the edge of observation, small differences matter. A slight shift in wavelength changes an age estimate. A subtle spectral feature alters interpretation. A careful calibration prevents confusion between signal and noise. Precision is not optional when studying deep time. It is the difference between insight and illusion. James Webb's design reflects this truth. Its instruments are tuned to listen quietly. Its environment is controlled to reduce interference. Its data is handled with care, shared openly, and examined from multiple angles. This approach reinforces another essential value: humility. The universe does not arrange itself to be easily understood. It does not adjust its behavior to fit expectation. It unfolds according to physical laws that remain consistent, even when their consequences feel unfamiliar. Humility in astronomy does not mean uncertainty without confidence. It means confidence that is earned, bounded, and open to revision. It means acknowledging when observation reaches its limit and allowing other tools to take over. James Webb has shown how powerful that humility can be. By clarifying where observation ends, it strengthens the role of theory, simulation, and inference beyond that point. It creates a clearer division of labor within science. Light tells one part of the story. Other methods tell the rest. This balance prevents confusion between what is known directly and what is understood indirectly. It keeps interpretation grounded. Perhaps most importantly, this clarity brings a sense of scale. The universe revealed by James Webb is vast beyond everyday intuition. Billions of years stretch between emission and arrival. Entire generations of stars live and die in the time it takes light to cross space. Galaxies assemble, merge, and transform long before their light reaches us. Standing within this scale does not diminish human experience. It contextualizes it. The same physical rules that govern the earliest galaxies also govern the matter that makes up planets, oceans, and bodies. The same expansion that stretches ancient light also shapes the space we occupy now. Time flows forward consistently, whether measured in seconds or billions of years. James Webb's observations anchor this understanding in reality rather than abstraction. They show that deep time is not an idea. It is something that arrives, photon by photon, into instruments built to receive it. And then, at the edge, the story changes. Light runs out. Observation stops, not abruptly but naturally. The universe does not close a door. It simply becomes quiet in a different way. This quiet is not emptiness. It is structure. It tells us that reality extends beyond what can be seen, and that seeing is only one way of knowing. It reminds us that the observable universe is not the whole universe, but it is the entire history that could ever influence us directly. That understanding grounds curiosity rather than leaving it unresolved. It allows wonder without confusion. It allows questions without insisting on answers that physics cannot provide. It replaces the urge to push endlessly outward with the insight to look carefully at what has already arrived. James Webb does not promise to reveal everything. It promises to reveal exactly as much as light allows. In doing so, it completes a long arc of inquiry that began when humans first looked at the sky and wondered what it meant to see distant stars. That arc now reaches the boundary where vision itself must stop. The boundary is quiet. It is stable. It is defined. And within it lies a universe rich enough to occupy curiosity for generations. Knowing where the boundary stands does not close exploration. It makes exploration honest. It leaves the listener not with unanswered mystery, but with a steady understanding of scale, time, and the physical rules that shape all observation. The universe does not need to be fully visible to be deeply known. It only needs to be listened to carefully where it still speaks.